Imagine a scenario where scientists were unexpectedly faced with a massive dichotomy. They were unprepared for the stunning revelation that emerged when they first glimpsed the far side of the moon. This hidden part of the moon, long unseen by human eyes, appeared completely different from the familiar near side, covered in countless craters that no one had anticipated. This discovery is not only reshaping our understanding of the moon but also prompting new questions. Space, once a vast mystery, is now being explored more thoroughly than ever before, thanks to advanced technologies like the James Webb Telescope. Join us on an extraordinary journey through space, where every new finding opens up a world of possibilities. For centuries, humanity has gazed at the moon, captivated by its beauty. Yet, despite our fascination and exploration, we have only truly observed one side of it. The other side, often referred to as the dark side of the moon, has remained largely unseen and mysterious. This is due to a phenomenon known as tidal locking, where Earth's gravity has slowed the moon's rotation, causing the same side to always face us. This means the side we cannot see from Earth is the far side of the moon. Occasionally, we can glimpse the edges of the far side due to a slight wobble called libration. In total, about 59% of the moon's surface becomes visible from Earth at different times, but the far side largely remains hidden. Contrary to popular belief, the moon does rotate. However, its rotation period matches its orbit around Earth, taking about 29.5 Earth days to complete both one rotation and one orbit, making its day and year the same length. The term, dark side of the moon, doesn't imply darkness in terms of light, instead, it signifies the unknown. Before spacecraft ventured around the moon, we had never seen this side. Both sides receive nearly the same amount of sunlight on average, but Earthshine, sunlight reflected from Earth, makes the near side slightly brighter. During lunar eclipses, the far side receives a bit more sunlight. The near side of the moon experiences significantly different lighting conditions compared to the far side. At night, when the Earth is full as seen from the moon, the near side receives about 10 lux of illumination, comparable to the light on a city sidewalk under streetlights and 34 times brighter than a full moon as seen from Earth. In stark contrast, the far side during lunar night gets only about 0.001 lux of starlight, barely enough to be noticeable. The entire far side becomes completely dark only when we see a full moon from Earth. The term, dark, also applies to communication challenges. Spacecraft lose contact with Earth when they go behind the moon, a problem encountered during the Apollo missions. This communication blackout is another reason why the far side is considered dark. The far side of the moon remains mysterious and intriguing, not because it is perpetually shadowed, but because it is largely unknown and difficult to explore. However, with advancements in space technology, we are gradually uncovering its secrets and revealing a world that has been hidden from us for so long. The differences between the moon's two hemispheres are striking. The near side is characterized by large dark plains known as maria, which early astronomers mistakenly believed were seas. In contrast, the far side is densely cratered and has very few maria, with only about 1% of its surface covered by these plains compared to 31.2% on the near side. Scientists suggest that this disparity might be due to a higher concentration of heat-producing elements on the near side, as indicated by data from the Lunar Prospector's gamma-ray spectrometer. Other factors like surface elevation and crust thickness also play a role, but don't fully explain why the far side's South Pole Aitken Basin, despite its low elevation and thin crust, wasn't as volcanically active as the near side's Oceanus Procellarum. One intriguing theory posits that these differences might result from a collision with a smaller moon that formed from the same giant impact that created our moon. This collision could have added a thick layer of material to the far side, contributing to its distinct characteristics. The chemical composition of the moon doesn't fully support the idea that the far side has more craters due to Earth's protection from impacts. Instead, the abundance of visible craters on the far side is primarily due to differences in lunar lava flows. On the near side, lava flows cover and obscure many craters, making them less visible. The National Aeronautics and Space Administration, NASA, notes that from the moon's perspective, Earth blocks only a tiny portion of the sky, meaning both sides receive a similar number of impacts. The near side simply has fewer visible craters because resurfacing lava flows have hidden them. Recent research suggests that during the moon's formation, the nearby Earth's heat kept the near side warmer for a longer period, delaying the solidification of the crust and resulting in a thinner crust. This thinner crust made it easier for meteoroid impacts to break through and release lava, forming the Maria. In contrast, the far side's crust thickened sooner, making it less likely for impacts to release lava. The far side of the Moon also features more extreme variations in terrain elevation, with the Moon's highest and lowest points and tallest mountains located there. Until the late 1950s, our knowledge of this hidden hemisphere was limited. Small wobbles in the Moon's orbit, known as librations, occasionally allowed glimpses of the far side, but only about 59% of the total surface was visible, and from such a low angle that distinguishing craters from mountains was challenging. One notable feature visible through libration is Mare Orientale, a vast impact basin nearly 1,000 kilometers wide, which wasn't named until 1906 and whose true nature was only discovered in the 1960s when images were projected onto a globe. The Soviet probe Luna 3 took the first photographs of the far side on October 7, 1959, revealing a landscape with fewer Maria than expected. These images allowed the creation of the first atlas of the far side, published by the Union of Soviet Socialist Republics, USSR, Academy of Sciences in 1960. In 1961, the USSR released the first globe featuring far-side lunar features based on Luna 3's images. Another Soviet probe, Zond 3, sent back higher-quality images in 1965, further enhancing our understanding of the Moon's far side. The second part of the Atlas of the Far Side of the Moon, published in 1967, was based on data from the Zond 3 probe and revealed 4,000 new features, including chains of craters, but still no extensive Maria. That same year, the first comprehensive map and an updated globe featuring 95% of the lunar surface were released in the Soviet Union. Many of the far side's features were named by Soviet scientists, who chose names like Jules Verne and Marie Curie. The International Astronomical Union later accepted many of these names. NASA's Ranger 4 was the first spacecraft to impact the far side on April 26, 1962, but it failed to send back data. The most detailed early survey came from NASA's Lunar Orbiter program from 1966 to 1967, with Lunar Orbiter 5 providing most of the far side coverage. The far side was first seen directly by human eyes during the Apollo 8 mission in December 1968, where astronaut William Anders described it as looking like a heavily used sandpile full of bumps and holes. All 24 astronauts from Apollo missions 8 through 17 saw the far side, and multiple lunar probes have photographed it since. Communicating with spacecraft on the far side is challenging because they are out of direct radio contact with Earth, a situation that caused tense moments during the Apollo missions until the craft reappeared. Geologist astronaut Harrison Schmitt lobbied for Apollo 17 to land on the far side, but NASA rejected the idea due to the risks and costs involved. In 2018, China launched the Qiuqiao relay satellite to the Earth-Moon L2 point to facilitate communication with the Chang'e 4 lander and U2 rover on the far side. This point is also considered ideal for a proposed propellant depot for future space missions. In January 2019, history was made when China's Chang'e 4 spacecraft gently touched down on the enigmatic far side of the Moon, marking humanity's first soft landing on this unexplored lunar territory. Equipped with advanced scientific instruments, including a low-frequency radio spectrograph and geological tools, the mission aimed to explore and study this unique region of the Moon. The far side of the Moon, unlike the familiar near side that constantly faces Earth, offers a unique sanctuary from terrestrial radio interference, making it an ideal haven for radio astronomy. This advantage allows astronomers to explore the cosmos without the disruptive hum of Earth signals. In a remarkable development, Chinese scientists unveiled high-resolution images captured by the lunar penetrating radar aboard the U2 rover in February 2020. These images provided unprecedented insights into lunar ejecta formations, revealing crucial details about the Moon's geological history and internal structure. Such revelations paved the way for a deeper understanding of lunar evolution and planetary dynamics. Building on these successes, the China National Space Administration launched Chang'e 6 in May 2024, marking another milestone with the first-ever lunar sample return mission from the far side's Apollo basin. This ambitious endeavor included deploying a mini rover for infrared spectroscopy and performing robotic rendezvous and docking maneuvers in lunar orbit. The mission culminated in the safe return of lunar samples to Earth, heralding a new era of lunar exploration and scientific discovery. Looking ahead, NASA and the U.S. Department of Energy are collaborating on the Lunar Surface Electromagnetics Experiment, LUSEE, lander, scheduled for potential deployment by 2026. This robotic observatory aims to explore the Moon's far side, measuring electromagnetic waves dating back to the universe's infancy. Such endeavors promise to uncover crucial insights into cosmic origins and the early universe's evolution. The far side of the Moon also presents promising prospects for future astronomical installations, including radio telescopes nestled within its serene, crater-dotted landscape. These installations could harness the Moon's natural shielding from Earth's radio transmissions, offering an unparalleled vantage point for observing celestial phenomena. However, significant challenges, such as dealing with the Moon's fine dust, must be addressed before these visions can be realized. The Moon's fine dust poses a persistent threat to equipment and instruments, necessitating innovative solutions for contamination control. Additionally, the materials used in constructing lunar observatories must withstand the harsh realities of space, including solar flares and cosmic radiation. Beyond scientific exploration, the Moon's South Pole Aitken Basin stands as a tantalizing target for future sample return missions. This colossal impact crater, spanning nearly 2,400 kilometers, offers a unique window into the Moon's geological past. Samples retrieved from this region could unlock invaluable insights into lunar composition and the cataclysmic events that shaped its surface. Moreover, the far side's Maria, shielded from the solar wind by Earth, harbor significant concentrations of helium-3, a rare isotope with potential applications in future fusion reactors. This valuable resource underscores the Moon's potential role in advancing sustainable energy solutions and fostering human settlement beyond Earth. In a groundbreaking new study, scientists from institutions around the globe have delved deep into the Moon's mysterious geological past, unearthing compelling evidence to shed light on the long-standing enigma of its dark side. The research, spearheaded by experts from the Earth-Life Science Institute at Tokyo Institute of Technology, the University of Florida, and other esteemed organizations, has revolutionized our understanding of lunar asymmetry. This asymmetry, characterized by stark differences between the Moon's near and far sides, has baffled astronomers for decades. Through a meticulous blend of experiments, sophisticated computer modeling, and detailed analysis of lunar surface data, the team uncovered a pivotal factor: radioactive elements. Elements like potassium, thorium, and uranium were found to play a crucial role in generating heat through their natural decay processes. This heat, in turn, melted the rocks where these elements were concentrated, leaving distinctive geological imprints across the Moon's surface. Dr. Matthew Larnaville, a prominent planetary scientist and co-author of the study, highlighted the importance of these findings in enhancing our understanding of the Moon's complex geological history.